Okay, let's take a look at another proof of the Pythagorean theorem. This is the proof that's known as Garfield's proof. And it was authored by a former president of the United States, Andrew Garfield. So again, let's kind of review what it is we want to show. Well, we want to show that if we have any right triangle of any particular side lengths, and those side lengths listed in order of magnitude are A, B, and C, then the following algebraic sentence is true: A squared plus B squared is equal to C squared. So let's go ahead and start with Garfield's proof. Garfield's proof proceeds this way. So this is what we want to show. And here's Garfield's proof over here. We'll go ahead and draw up our general right triangle. I'm going to make it a 3, 4, 5 just for purposes of ease of drawing. Actually, I'm going to make it, I guess, a 6, 8, 12. But in general, we can think of this as any A, B, and C. And the idea with Garfield's proof is that we make two copies of these and put them together in a very special way. So the copies are put together in this format. First one is put down in sort of a horizontal sense, where this A is laid horizontally and B is vertical. So let's see, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that's the original triangle copy. Again, this is shortest and longest side. And then it's copied in the same I guess, horizontal and vertical sense, but now with A being vertical and the points touching here. So 1, 2, 3, 4, 5, 6. So we have a right triangle here whose A by B by C. And then kind of the ingenious thing that Garfield does is go ahead and add that line in. Why not? And you get these three right triangles, two of which are copies of the original, and one of which appears not to be a copy of the original. Now, if we go back to the original, we can think of this as having angles 1 and 2. So that means that the angles here will be 2 and 1, and here again 2 and 1. So it's some concern about what is this piece right here, and if we look inside, it's obviously a triangle. What type of triangle? And just kind of eyeballing, it seems like it's a right triangle, just looking at the corner of my straight edge. And that conjecture can be validated by virtue of the fact that the two non-right angles of the right triangle and the original are complementary, or add to 90 degrees. So 1 plus 2 here would add to 90 degrees, which leaves exactly 90 degrees for that angle there, if this is to be a straight line. So indeed, it is a right triangle, and this right triangle, of course, has a base and a height equal to the hypotenuse length C. And so Garfield's proof is an area-based proof, and the area is calculated two different ways. The first way is to consider parts and pieces. Here we have two triangles of the original size, so this triangle and this triangle, and they both have a base that can be calculated as the area can be calculated as 1/2 the base times the height, or 1/2 b times a in this case, or a times b. Since multiplication is commutative, of course, you can write it either way. And then we have another right triangle here that's connected up, and so that figure would be 1/2 c times c for base times height. So the area calculated one way, of course, 2.5 make just 1, so this would be ab plus 1/2 c squared. The area can be again calculated a second way by considering this figure as a whole, and in this we have to consider what type of figure it is, and since we have supplementary angles along what can be considered a diagonal of two lines, that's enough to show that these two lines, top and bottom, are going to be parallel. They're both at a right angle to the straight line that's formed by the union of side A and side B, which meet, we think, here at, or we know here, at a straight line. So if this thing is a trapezoid, you can use the trapezoid area formula, which is 1/2. Let's see, it's base 1 plus base 2 times the height of the trapezoid. And now we have to kind of identify what base 1 and 2 are. Remember, these are the lengths of the two parallel sides. So it would be 1/2. Base 1 is B, just our B. And base 2 is A, our A up there. And then the height itself is this whole distance, and that height is A plus B. So if we multiply that out, we get 1/2. Let's go ahead and distribute the binomial. It's going to be AB plus B squared. I'm going to distribute the B, and it'll be A squared plus AB when I distribute the A. So it will be 1/2. Let's go ahead and write things in sort of alphabetical order. A squared plus 2AB plus B squared. And that will be the same as 1/2 A squared plus 2AB. Well, 2AB divided by 1 divided by 2 would just be 1AB plus 1/2 B squared. Again, we notice that, well, we've calculated area two different ways, so these two areas have to be the same. So if area 1, I should say if area 2 is equal to area 1, let's go do it that way, then this expression must be equal to this expression. So I'll sort of put stars next to those. So if those two expressions are equal, perhaps we can squeeze out the formula. So here we go. A2 would be, I think I can fit it down here, 1/2 A squared plus AB plus 1/2 B squared. So that's my A2 area. And A1 is AB plus 1/2 C squared. And right away what we notice in this particular equation is that AB and AB are both factors, or I should say pieces on either side of the equal sign that we subtract an AB from both sides and they cancel. So what happens when I cancel those out? I get a 1/2 A squared plus a 1/2 B squared equal to a 1/2 C squared. Now if I multiply both sides by 2, I end up with A squared plus B squared equaling C squared. And we have demonstrated that indeed, given a general right triangle, we can prove that A squared plus B squared is equal to C squared.